Good morning, afternoon, middle of the day, everyone. It is my great pleasure today to introduce you to Dr. Juliana Saponara, who will be giving a seminar. And just as a brief introduction to her, she obtained her degree in astronomy from the Facultad de Ciencias Astronómicas y Geofísicas at the Universidad Nacional de La Plata in Argentina. She completed her PhD at the Instituto Argentino de Radioastronomia in La Plata as well. And she now works there as an assistant researcher and as a professor, right? You're teaching.
Yes.
So she has a lot to do. As a radio astronomer, she has had the opportunity to visit the GMRT in India and the ATCA, the Compact Array in Australia. And her research focuses on galaxy evolution, particularly the role of neutron hydrogen in shaping galactic environments. And I know this is a topic that interests a lot of us at the IAA as well. And I'm not sure if she's going to be doing this part that comes next in her talk, but I would be very excited to see it because she also enjoys performing scientific stand-up comedy as part of her outreach activities. Some pressures on that. So today she will talk about MeerKAT imaging, another topic that is really interesting for a lot of us. So thank you for coming, Juliana, and writing the report to you.
Okay, thanks for your introduction. I'm very glad of being here. So in this presentation, I will talk a recent publication we made with Barbara Koribalski, Cheyenne English, and Pedro Mire. We analyzed high angular resolution radio continuum data from MeerKAT of 3 different groups of galaxies, which are at different stages of their evolution. But before that, I want to tell you that I'm from Argentina. This is a Google map picture. Those are our country neighbors. This is a picture of myself in Ushuaia. I don't know if you know, but this is the southernmost city in the world. That's why it's called the end of the world, fin del mundo. And the balloons shows different telescope we have in Argentina. It is also marked there where is the institute where I work, the Instituto Argentino de Radioastronomia, and la Universidad de La Plata, where I obtained my degree, which is, La Plata is a city which is nearby Buenos Aires. And here I chose some pictures. This is one of the 2 30-meter antenna we have at the Institute. Now, this antenna, at first, they were built to observe H1, but nowadays there is a group observing pulsars, and they're working on that. The one over there is the telescope Casleo. It's an optical telescope, which is close to the Andes. And this one here is a telescope we have at the observatory. Nowadays, it's not used for science. As you can see, it's very, very old. It's just for visitors. So if you go to La Plata and want to visit and observe with this, on Fridays, you can. I also put some pictures of Argentina, like the waterfalls, Fitzroy, if you like do some trekking. And okay, so I said that we study this group of galaxies. So why it is interesting to study them? Because we know that are the most common environment where we will find galaxies is intermediate density environment, because you can find the galaxies isolated or in clusters will be a high density environment. And also because our local group is a group, our environment where the galaxy is a group, is the place where we have the best chance of observing the galaxies that are emerging, interacting due to the low relative velocities of this, and are the building blocks of bigger structures. So here I'm showing you 4 different groups of galaxies. Centaurus A, this is not a picture of the group, it's just the Centaurus A galaxy, but it's a combination of radio continuum, where you can see the shapes, the lobes, also the optical, where you see the dust lane and this diffuse brightness of the galaxy. This is Andromeda as an example of the local group, okay? And IC 1459 is the first group I studied. I will tell you something about this group later, but not later, in the next slide. And a Hickson compact group, because I know you work with this. Okay, So, and the definition of the group, right? It's just tens of galaxies within 1 megaparsec, 2 megaparsec. So during my PhD, my postdoc, I work with H1 line emission. So this is IC14, this one. Here it is. This is the inner part of the group. It contains 11 galaxies. So we use this ATCA data. The contours are the H1, and we found this huge amount of H1 debris, which at the distance where this group is, it expands over 250 kiloparsec. And another interesting thing is that the amount of H1 mass present in the debris is 3 times the amount of the H1 mass that this galaxy has. So that's a lot of H1. And well, see, you can see this galaxy is clearly disrupted in there. I also studied this peculiar one. It's peculiar for me, right? But because this galaxy belongs to this small group, where this main galaxy of the group is this one.
Sorry, maybe you can use the mouse.
Yeah, you're right.
People that are online or
sí. I was thinking about this, but then I thought that I probably will be like doing this all the time. So this galaxy in here is similar to the Milky Way galaxy. And we focus on this particular one. It's a dwarf galaxy where the H1 is displaced from the stellar counterpart. And at the distance where this galaxy is, this displacement is 4 kiloparsec. So we were trying to understand why is this happening, and it's not the star forming activity of the galaxy. It's because it is interacting with the main one. And another thing is we proposed this as a candidate of dwarf transition galaxy, becoming from gas-rich one to a gas-poor. And the one in here is the galaxy Forcade Figueroa, which is an ultra-thin galaxy, was discovered by an Argentinian and Chilean astronomers, and was first detected in H1 with this antenna I showed you before, the one that are at our institute. But now we observe with GMRT and ATCA. We combine this data, and the main question to ask is why it remains super thin. So we perform the mass modeling of it, looking for different dark matter distribution halos, and we find that Navarro, Frank, and White is the best to reproduce the fitting of the rotation curve. So probably this is the main reason why the compactness of the dark matter distribution. So, okay. So a few years ago, Barber proposed, invited me to be part of this proposal to observe these 3 groups of galaxies with MeerKAT. And I say, of course, I want to be part of this. And when I saw the radio continuum images, I thought, okay, I want to learn, what can I learn from the radio continuum data? Because until that moment, I focused on H1. So these are the 3 groups. Those are cutouts of the radio continuum images we used for this work. So the first one, we consider that it is in an early stage of the group evolution. Because it's a galaxy pair, there are a few dwarfs detected in H1. The one in the middle is in an intermediate stage of the evolution of groups, and it contains this one that is a merger, this galaxy that has these tails. There are around 12 or 13 galaxies with different morphologies in this group. And then this one is the one that is in a more evolved stage of evolution. So most of the galaxies in here are spheroidals. I choose this one because it's beautiful. Because the rest of the image maybe is not as much interesting. And so we were seeking for evidence of the environmental impact by using the radio continuum data and infrared data. So I will go toward this now. So I started to learn what can I learn from the radio continuum emission. So we know that the galaxies, normal galaxies, when we detect this emission is a mix of two different processes: bremsstrahlung, which is thermal, or also you can find it as a free mechanism, and non-thermal emission, which is synchrotron. So in bremsstrahlung, the thermal, this emission is produced by a charged particle that is deaccelerated by the interaction with another charged particle. So, for example, we will see this emission coming from H2 regions. And non-thermal, which is this synchrotron, we have this emission is produced by relativistic cosmic electrons spiraling around the magnetic fields. I succeed pronouncing all these words. So, for example, we can detect this from supernova remnant. So, okay, it's a mix. So, is it possible to distinguish which part of this emission is coming from which mechanism? So, it's not straightforward. It's not easy at all. What we know is that if we are considering this optically thin regime, so we are okay because we are observing at 1.4, 1.3 gigahertz. So the spectral energy distribution of bremsstrahlung will be flat, and the spectral distribution of non-thermal will be steep. And here you can see a few numbers of reference. So we can define this, we can use this parameter, which is the spectral index, which is defined in terms of the integrated flux density at the frequency. So we are using this convention. And here I wrote some numbers, like it is known that if I told you that thermal will be flat, so this value will be around minus 0.1, and if it is coming from non-thermal emission will be between minus 0.5, minus 1 point something. Okay. So I started to look at the bibliography and I found this infrared radio correlation, which I will mention in the next slide. So if we want to study the star formation activity of these galaxies, because we know that is the main internal process that will be shaping the evolution of the galaxies, we are looking into the ESM. So we know that the H1 is the main fuel for star formation. We need the molecules. Then we need the dust to protect those molecules. So, for example, in ultraviolet wavelengths, we see O and B stars, which are the youngest, the brightest. And these photons, these ultraviolet photons, will be absorbed or scattered by dust, and then we will detect this at the infrared wavelengths. For example, here in this band, the band 3 of WISE at 12 microns, will be detecting these molecules, the PA, the polycyclic aromatic hydrocarbons, and this band 4 is produced by this, the small dust rings, and in band 1 and 2 will be detecting the rest of the old population of the galaxies. So I took this from Share 2013. So I am introducing this because the infrared data we use is from WISE, and we make focus on this band, in the band 3, because the angular resolution of this band is quite similar to the angular resolution of our radio continuum data. Okay, so the first ones who published this tight correlation between the infrared and the radio emission were Hello, Seufer, Rowan, and Robinson in 1985. This is the plot I took from the paper. Those galaxies were spiral galaxies. So they find this nearly correlation, extremely tight, over 3 orders of magnitude and propose this Q parameter, which is the ratio between the infrared and the radio emission. So they concluded that this infrared dust heating and the synchrotron emission are both powered by massive star formation. Some years later, in 2001, Young, Reddy, and Condon have a bigger sample of galaxy, 1,809. They keep finding this correlation, and they measured a mean value of this parameter Q and 2.34. And they demonstrated that the radio continuum is a reliable tracer of star formation across a wide luminosity range. Okay, but so now the question is, what happens if galaxies don't follow this? When they are not correlated, let's say. So we find this, in which cases they will not follow this. So in 2021, Del Vecchio and collaborators published this, where they found that using 4,000 star-forming galaxies at different redshifts, that there is a dependency on this parameter Q and the stellar mass of their galaxies. So the more massive galaxies are, the lower is this Q parameter diff. So they interpreted this as saying, okay, if the higher the galaxies have higher mass, then the higher will be the stellar formation rate, because of the higher will be these surface densities, the stronger the magnetic fields, and more efficient for cosmic ray confinement. I choose this to show you a work where in Tabatei 2013, when in this paper they took this galaxy and tried to decompose the thermal and non-thermal component by modeling using Herschel data the thermal component of the galaxy, and they found this is a map, a pixel by pixel map of this parameter, where they do this ratio between the infrared and the continuum, the radio continuum data, and they find this, that where in the star-forming regions, this synchrotron spectra is flat, and it will be steep in the magnetic arms, and these are a clear evidence of the aging and how it is the propagation of these cosmic ray electrons. Okay, so another peculiar case is this. This was published by Condon in 2002. So this is a pair of galaxy, a kind of a taffy system. And the interesting thing of this is that there is a bridge between the two galaxies, and the spectral index in this bridge is minus 1.3, which is steep, and the Q parameter is low. And this is the last paper I will mention as a background for our work, is this published by John Nevsky and Prodanovic, where they classified in different merger stage of the galaxies. And look, I will tell you more about this classification later, but they look if there is any relation of this merger stage with this Q value, and they found that in the early stage of the interaction, there is an enhance in the far infrared emission, and then so the spectra will be the spectral index will be flatter and Q will be higher. In the mid stage, then there will be an excess in synchrotron emission. Then the alpha will be steeper and Q will be lower. And in the late stage, we have the far infrared rises again, then Q returns to be more standard, which is 2.3, 2.4. So based on all these things I found in the literature, I look into our data and see what we found. Okay. So the three groups we observed with MeerKAT are the following. I told you before. One thing I want to mention here is the bandwidth, which is 856, which is wide. I am telling you this because the spectral index we derive, we're using the bandwidth. It's an in-band spectral index. So the first one, all the three groups of galaxies were previously studied by Kolovalsky and Cheyenne, and they have they have a lot of H1 degrees among the galaxies. Okay, so this is the first one. I told you that is a galaxy pair with at least three dwarf galaxy identified in H1, but let's say at least because with the new data we know other things. So this is the radio, it's a cutout of the radio continuum image we used to work. So the first time I saw this, I was amused because of the amount of sources that you can detect with 4 hours observations of MeerKAT. It's amazing. Well, the other group is this one, NGC 3263. Sometimes it is also named as 3256. The thing is that this group also contains 3 subgroups, which are difficult to distinguish which galaxy is part of which group because the velocities are the difference in velocities are less than 2,000 kilometers per second. So in the literature, you will find that this galaxy belongs to here and there, and well. The interesting thing is here, this cloud, which is named the Vela cloud, discovered by English in 2010. So this is the cutout of the radio continuum data. So this is the merger. This is the galaxy with the tail. Well, those are galaxies that belong to the group. There are many sources in there. And the one that is in the more in the late stage of the group evolution is this one, where the interesting thing is this huge amount of H1 in here. Okay. So what we sorry, I forgot this one. The cutout of the radio continuum image we use. So here I'm showing you 5 of the galaxies. These 2 first are the ones that are interacting in the galaxy pair. This is the one that is in the more evolved group. And those are for NGC 3250. This is 3255, the one that is a merger. This is the one that has a tail. So in the grayscale, I'm showing you an DFS image, and in white and black, the contours are the radio continuum detection. So what I found to be the same for all the galaxies is the WISE data. So I learned how to do the photometry. So I will not talk much about this, but I wanted to do it by myself, so I can say, okay, I have done all these things in the same way. So, okay, so I fight a lot with units. I thought that I will not have this problem as a researcher, just only during my degree, but it's not true. And the first plot I'm showing you of our results is this, is the Wiles color diagram. Black line traces the star formation sequence defined by Jared. So all the galaxies that are not following this, so something is, let's say in this way, something is going on with them. And here is the place where the merger appears. Those are in blue are these two galaxies that are interacting. So I use blue for the galaxies in the first stage of the group evolution. In yellow are the one that is in an intermediate, and red is the galaxies that are in the late group. Then we do this plot to check if they follow the infrared radio correlation. So we make this fit. The fit is quite linear because it's 0.99. So the mean value we find is 2.5, and I use this. It is written this here, W3PEH, because of what is explained in here. So we follow what is being proposed by Clover, I don't know how to pronounce it properly, sorry, 2017. They proposed this method where we extract this 15.8% of the band, the first band, which is the one that is when we are detecting the more evolved stars from the band 3. Okay. And there is just one galaxy that is 3 times away from the relationship, which is this ISO, this galaxy here. So probably because, well, this belongs to the more evolved group, and probably she has already consumed all the gas. So the star formation properties, the star formation rate estimated with the this band 3, just considering the PAC contribution versus the star formation rate estimated using 20 centimeter, our radio continuum data, is quite good. The relation is okay, I mean. We performed the set fitting, but just for 8 galaxies. So those are like preliminary results, because the points we have to perform the set fitting are just 5. But we did it to estimate the stellar mass of the galaxies, and also you can obtain the star formation rate. So in this plot I am showing you here, there are these are main sequence curves that were estimated in 2 different ways. One is the one that is published by Spiegel 2014, where they consider different redshift, galaxies at different redshift, and estimated this curve. And the other one, Leslie 2020, using different estimators for star formation rate. Well, so the thing is, the galaxies that are interacting are above this curve, and these other ones that are here are not forming stars as one expected them to form. Okay. And we also look into this degree of interaction. So we follow this numerical classification. The people who published the other paper I told you about use the same one, this proposed by Han 2011. Yeah. So 0 are those which are not interacting at all, or they are not merged, but they are not interacting at all. Then the number 1 are for galaxies that are separate and they are not showing any asymmetry or tidal tails. Then 2 for those that we can see that maybe one arm is more open than another, or they are showing some kind of asymmetries in their disk, or tidal tail. So we separated this in 2 and 2.5 to distinguish the ones that just have some morphology asymmetry, or the ones that have tails, or the bridge. And the third is the one that is a merger, and it has 2 nuclei. I will say something about this later. But we don't find any kind of trend in using this classification with the Q value. So it's not the same as Donovsky and the previous author found. But we have a less amount of galaxy too. So these are the last slides. I am showing you the results of some particular galaxies. This is the one that is a merger. So you can see here in this optical image, which was obtained with the optical telescope in Australia, then it has these tails. They are also can be observed in H1. English published it in 2003. This is the DSS. This imaging I'm showing you here, the DSS in grayscale, with the radio continuum contours. So Norris and Forbes in 1995 identified 2 different nuclei in this galaxy. So here are the spectral index, the in-band spectral index we derive from this galaxy. So the global value is minus 0.9. These values here, which are with this violet plum color, are not okay. Those are errors in our images, but the rest we trust. Sorry. Okay, wait, they are here. So this is the error map to show you. In some places, the spectral index is minus 0.6, sorry. And this is the Q map I told you before. So this, sorry, the global value of this is 2.5, and in here you can see where this nuclei are. This value is 0.5, which is clearly a radio excess in this region, and is pointing towards this AGN activity, which is in agreement with the publication made by Juliana in 2015. So the next 3 galaxies I will show you are interacting among them. They are probably the ones that originated the Vela cloud in H1. So this one, the global spectral index is minus 0.8. It is not super phasons. The inclination is 73 degrees. So here in this part is where the spectral index is more flat. And the global value of Q is 2.4. So here it also shows what we were expecting, except for the global spectral index, which is steeper, minus, sorry, there's an error there, minus 1.5. And This is the one with the tail, which is almost L-shaped. So this is quite interesting, this tip in here. So the spectral index map is flatter here, but so if we look into the error map, we know that the error is high, but also this Q map shows that value of 2.0. Another interesting thing is the spectral index is flatter where the stellar disk is, and as long as you move away from the disk, it becomes more steeper. And the last two are this one, which is one of the galaxies that are interacting. So this clumpy region is coincident with an H2 region, which suggests recent star formation. And here, this is the same clumpy region where the spectral index is flatter. And another interesting thing is when we look into this Q map, it also shows a radio excess in the center part, pointing towards the existence of an AGN, a low luminosity AGN. And this is the other one, which is interacting with the previous one. So where the spectral index is minus, the global spectral index is minus 1.2, and the Q value is 2.4. Okay. So as a summary, we work with these three groups of galaxies, which spans over different evolutionary stages. We found that in the interacting pair, the star formation is high and the spectral index are steeper, minus 0.5, minus 1.5, minus 1.4. In the group that is in the intermediate stage, we find a lot of different things like the merger, the galaxy that is in a merger system, the ones that are interacting. The star formation rates are from one that is not forming stars to the ones that have a high star forming activity. And in the late group, most of them have low star formation rates. And this thing that we detect with this Q map, these two low luminosity AGNs, which seems to be something interesting to follow up in next studies. So that's all. Thank you.
Thank you, Juliana. Very interesting. I have a lot of info. Are there any questions from the audience here? I have one.
Okay.
Sorry, go ahead.
Thank you. You said that you measured in-band spectral indices from
Yes.
MeerKAT. How confident are you that those values are reliable? Because I was interested in some galactic sources with thermal spectral indices, for which there are MeerKAT data, and somebody working on MeerKAT told me to be careful with those values. So, are those problems solved? Or
Well, okay, so it was tricky to determine these spectral indexes. But I am confident with the results because this gradient we observed, okay, so the errors are high, but the gradient we observe in the galaxies are close similar to those published in Changes. And you have many more galaxies. So that's the reason I am confident with the values. I find some things that are similar to others. And those are kind of hints, right? So all this work is, okay, if I find this, and which makes sense, and another thing, and this, well, okay. So with all this information, everything points toward that result. But it was tricky.
That was exactly the question I was going to ask. I was wondering whether.
Just telling you, there is a question in Zoom as well.
Okay.
When you finish.
Yeah, no, because it was connected. I was just wondering exactly how you derive them, because you mentioned changes, and we actually had some issues with our in-band spectral index, and we were forced by referees to make a really big expose on how reliable they were.
Okay.
And so it is always a good thing to compare to also band-to-band spectral index from other sources if it is available or possible. Yeah, anyways.
Well,
That's just my
I'm gonna just add on that. I didn't catch why you wouldn't trust the values from MeerKAT. I didn't get it.
No, because I think it's because the errors are high in the determination of them. No,
It's
and also
sensitive to, yeah, it's very sensitive to potential artifacts in the radio continuum data. We noticed that in changes with the VLA data. So you can get, especially in the edges of your spectral index map, you can get quite crazy numbers or blobs that stick out that are due to potential artifacts.
yeah, so when I decided which channels I will use for the combination, I was careful the images I was obtaining are pretty good with no artifact, except for NGC, the merger system, which it has a lot of artifacts. So that's why I was saying, okay, I don't trust in these numbers. And also I only trust in the ones in the galaxies that are the brightest galaxies.
Ismael, you can open your mic and let's see if we can hear you.
Yeah, can you hear me? Hello?
Pick up. That was
There is an echo. Yeah. Can you hear me?
¿Dónde está el micrófono esto?
Hello?
Prueba a hablar.
Hello, can you hear me?
No, no te escuchamos. Escribe tu pregunta en el chat y yo la paso.
What about now? Is working? Is working? Okay.
Okay, he's writing. But when he writes, I want to ask you, you mean the set with only 5 points?
Sí.
Do these galaxies have visible spectral, visible information? Can you do?
Yes, our next plan is to work with this pair of galaxies, the ones that are interacting. So for these galaxies, there are a lot of data at many different wavelengths.
Mm-hmm.
So we are planning to study this.
Next.
Yeah, because we were not able with this information when we performed the set fitting to see the contribution of the AGN or model this. So we want to do that.
Okay. So the Ismael Garcia is asking, no, he's saying thanks for the great work. I was concerned about the use of WISE data for tracing PHAs. In particular, the W3 band is super broad and include many other features such as silicates.
Okay.
Can you comment?
No comments.
No comments.
No comments. No, okay, I will. Maybe he can contact.
He says, he adds that silicates may be huge in NGC 3256.
Okay. Well, can you contact me?
He said that he will do that.
Great, thanks. That's good.
A follow-up question on that. Have you looked at Spitzer or James Webb, because James Webb have a pH?
Yeah.
So
I know. Yeah, but some of these galaxies has been observed and they have this data, but others no. So I was trying to be the homogeneous standard, homogeneous possible.
But probably many of these galaxies are in the Funks survey, right?
Some of them are, some others no.
And those that are, have to compare it, and do the result make sense, or in the sense of contamination?
No, I haven't checked that.
Nice.
Yeah. Sure. Thanks.
Now, my question was a bit related to that. So since you only have 3 groups here, are you confident about your conclusion because they are in agreement with previous results? Also, if some of the galaxies that you have, if not only this, but if you have previous, if you have seen results from previous groups, and they kind of agree with what you are having here.
Well, what I find in here, I think it makes sense at least. So that will be a good idea to check, to increase the sample and check.
By result, I mean, sorry, I didn't specify. By result, I mean the star formation trend that you see when you move from phase 1, intermediate and late phase. Is this something that you knew before that you're expecting, or is it?
No. Yeah, yeah, no.
Any more questions? Yeah.
Thank you very much for the talk. Interesting also, if you have some of the sources are resolved and the spectrum is, the edges we know are problematic, but you can differentiate between the core, the most central region, and the rest of the galaxy. And they try for search for hints, although you only have one band, it's broadband, of absorption, for example, briefly absorption in the nuclear. Or
yeah,
you may distinguish sites where you can enhance the formation.
That will be nice. Yes. Thanks.
Can I just ask super quickly, what kind of RMSs are you reaching with your 4-hour observations?
7 microshansky per beam. It's 4. Yes, that's amazing. It's really amazing.
Yeah. Well, that's thank Juliana again.
Now I will perform a stand-up comedy. Nah.
Then I keep the YouTube transmission.
No. It was a joke.